Neutrinos are everywhere. Billions of them are passing through your body right now. They stream from the sun, our own star. They are created in distant, exploding stars called supernovae. They were even made in the Big Bang, the very beginning of the universe itself. Yet, we cannot feel them. They are like tiny ghosts, interacting with almost nothing. They can travel through the entire Earth without hitting a single atom. This strange, elusive nature makes them incredibly difficult to study. Scientists have built enormous detectors deep underground, just to catch a fleeting glimpse of these ghostly particles, as they occasionally, very rarely, interact with matter. It is this ghost-like quality that makes them so fascinating and so important to understand. These particles are truly fundamental. They are part of the standard model of particle physics. This is our best description of the building blocks of the universe. The model includes particles you might know, like electrons and quarks, which make up atoms. Neutrinos are in a family called leptons, along with electrons. But unlike their charged cousins, neutrinos have no electric charge. This is a key reason they are so unsociable. Without a charge, they are not pushed or pulled by electromagnetic forces, which govern most interactions between particles. They only feel the weak nuclear force, which, as its name suggests, is incredibly feeble and only works over tiny distances. For a very long time, we thought we knew all about them. We thought they were not just ghostly, but also massless. The original standard model was built on this assumption. It seemed to fit the data we had. A particle with no mass would travel at the speed of light, just like a photon, the particle of light. For decades, this idea seemed correct. It made the mathematical models of the universe simpler and more elegant. But science is a process of questioning, and a puzzle emerged from the sun that began to challenge this long-held belief. The number of neutrinos we detected coming from the sun was far less than our theories predicted, a mystery that baffled scientists for years. This discrepancy, known as the solar neutrino problem, suggested something was wrong with our understanding. It hinted that neutrinos might be changing as they traveled from the sun to the Earth. They seemed to be oscillating or morphing between different types, or flavors. There are 3 known flavors of neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. The only way they could perform this incredible disappearing and reappearing act is if they had mass. A massless particle cannot change its identity. This discovery, that neutrinos do indeed have mass, was a revolution. It broke the standard model and opened up a whole new realm of physics, a world beyond what we thought we knew. The discovery that neutrinos have mass was a landmark moment in physics. It came from experiments like the Super Kamiokande detector in Japan. By observing neutrinos created in our atmosphere, scientists proved they were changing flavors. This oscillation is only possible if at least 2 of the neutrino types have different masses. It means that neutrinos must have mass, however small it might be. This was a profound realization. It was the first solid experimental evidence of physics beyond the standard model. Our neat and tidy picture of the universe's fundamental particles was incomplete. A new chapter in our cosmic story had begun, one that required us to hunt for this tiny but incredibly significant mass. But knowing that neutrinos have mass is not the same as knowing what that mass is. Oscillation experiments are brilliant at measuring the difference in mass between the neutrino types, but they cannot tell us the absolute mass of any single one. It is like knowing the height difference between 3 people, but not knowing how tall any of them are. Are they all very light, or is one much heavier than the others? This question is one of the biggest in particle physics today. Knowing the absolute mass of the neutrino would not just fill a gap in our tables of data. It could help us solve some of the deepest mysteries of the cosmos, from the structure of galaxies to the very nature of matter itself. This is where the Katrin experiment comes in. Located at the Karlsruhe Institute of Technology in Germany, Katrin stands for the Karlsruhe Tritium Neutrino Experiment. It is a gigantic, incredibly precise instrument designed to do one thing: weigh the neutrino. It is essentially the most sensitive scale in the world, built for the lightest particle we know of. Unlike oscillation experiments, Katrin does not watch neutrinos change. Instead, it uses a completely different direct method. It looks at the decay of a radioactive element and measures the energy of the particles that are released. It is a wonderfully clever and direct approach to tackling this fundamental cosmic question. The experiment itself is an engineering marvel. Its main component is a massive spectrometer, a 200-ton stainless steel vessel that is 24 meters long. It had to be transported on a barge and then by road in a delicate, slow-moving operation that captured public attention. This enormous scale is necessary to achieve the extreme precision required for the measurement. Inside this giant machine, scientists create a vacuum better than that in outer space and use powerful magnetic fields to guide particles. The entire setup is a testament to the lengths we will go to in our quest for knowledge, to measure a property of a particle so small and so elusive that it seems almost immeasurable. The heart of the Neutrino experiment is a process called beta decay. Specifically, it uses a radioactive version of hydrogen called tritium. A tritium atom has 1 proton and 2 neutrons in its nucleus. This nucleus is unstable, and after some time, one of its neutrons will spontaneously transform into a proton. When this happens, it releases 2 particles, an electron and an electron antineutrino. This is beta decay. The total amount of energy released in this decay is fixed. This energy is shared between the electron and the antineutrino. It is like a parent giving a fixed amount of pocket money to 2 children. If one gets more, the other must get less. Neutrino's strategy is to measure the energy of the electrons with extreme precision. Because the total energy is fixed, if the electron flies away with the maximum possible energy, there is almost no energy left for the neutrino. This maximum energy value is called the end point. If neutrinos were completely massless, the electron could, in theory, take away all the decay energy. But because the neutrino does have mass, it must always carry away at least a tiny amount of energy, equivalent to its own mass according to Einstein's famous equation, E equals mc squared. This means the electron can never quite reach that theoretical maximum energy. The neutrino's mass effectively steals a tiny bit of energy from the electron. So the scientists at Neutrino are not looking for neutrinos at all. They are looking for the telltale signature of the neutrino's mass in the energy of the electrons. They meticulously measure the energies of billions upon billions of electrons from the tritium decay. They are especially interested in the electrons right at the very top of the energy spectrum, the most energetic ones. By studying the precise shape of this energy spectrum near its endpoint, they can figure out how much energy is missing. This missing energy tells them the mass of the neutrino. It is an incredibly subtle effect, requiring fantastically sensitive equipment and painstaking analysis of huge amounts of data. Recently, the Neutrino collaboration announced a new groundbreaking result. After years of collecting and analyzing data, they have pushed the limit on the neutrino's mass down even further. Their latest findings show that the mass of the electron neutrino cannot be more than 0.8 electron volts. For context, an electron volt is a tiny unit of energy. The mass of a single electron is over 500,000 electron volts. This new upper limit is a remarkable achievement. It is the first time a direct measurement experiment has entered the sub-electron volt territory. This was made possible by improving their techniques, reducing background noise, and running the experiment for longer to gather more statistics, refining our cosmic scales. This new, tighter limit on the neutrino's mass from Neutrino is hugely important for science. It begins to close the window on what the neutrino's mass could be, providing crucial information for theorists who are trying to build the next generation of physical theories. Every new, more precise measurement helps us to refine our models of the universe. It rules out some theories and strengthens others. Knowing the neutrino's mass scale will be a critical piece of the puzzle for extending the standard model, perhaps pointing the way to a grander, more complete theory that unites all the forces of nature and explains why particles have the masses they do. The mass of the neutrino also has profound implications for cosmology, the study of the universe as a whole. Even though each individual neutrino is incredibly light, there are so many of them in the cosmos that their combined mass could have a significant gravitational effect. They could have influenced how galaxies and large-scale structures formed in the early universe. The more massive the neutrinos are, the greater their gravitational pull would have been, slowing down the clumping of matter. By pinning down the neutrino's mass, Neutrino helps cosmologists to fine-tune their simulations of the universe's evolution, leading to a more accurate picture of how we got from the Big Bang to the star-filled cosmos we see today. Furthermore, the nature of the neutrino's mass is itself a deep mystery. We do not know why it is so much lighter than all the other fundamental particles. One popular theory suggests that neutrinos are their own antiparticles. This would make them a unique type of particle known as a Majorana fermion. If this is true, it could help explain another great cosmic puzzle: why there is so much more matter than antimatter in the universe. Measuring the neutrino's mass precisely is a stepping stone towards experiments that could test this extraordinary idea. The Catrin result by constraining the mass indirectly guides our search for this new physics. The work at Catrin is a beautiful example of human curiosity in action. It is a quest driven not by the need for a new gadget, but by a fundamental desire to understand the universe at its deepest level. By building this extraordinary machine to weigh a ghost, we are not just measuring a number. We are testing the limits of our theories, peering into the history of the cosmos, and seeking clues to the next great breakthrough in our understanding of reality. Each new result, each tightening of the limit brings us one step closer to a complete cosmic blueprint, a final theory that explains it all. The journey is far from over, but the path